Hi everyone, I'm Miso Kim. I'm up there yet? Okay. So I'm Miso Kim from Korea again. So I'm here today to introduce Professor Zheng Liu. It is my great honor to have this opportunity to introduce our ACS Nano Rising Star today, Professor Zheng Liu. So Professor Zheng Liu is an associate professor at MSc and Triple E and Nanyang Technological University, Singapore, and he works on the synthesis of high quality and large size novel 2D monolayers, especially transition metal dichalcogenides, and their applications in electronics and catalysts. And he will cover the topic today, I am sure. And he is a recipient of numerous awards here. So here I will list a few. So he's the finalist of the World Technology Award in Energy category and Singapore NR Fellowship and NTU Nanyang's Assistant Professorship and Icon 2D Med Young Scientist Award in Singapore Young Scientist Award and Asia's Rising Scientist and Nano Research Young Star Editors and Nanyang Research Award and Highly Cited Researcher. And he was also named as the Materials Research Society of Singapore Chair Professorship at NTU, and he will add one more today as a rising star from ACS Nano. And here we are welcome to have Professor Zheng Liu, and the stage yours.
Okay, can you hear me?
Yes.
Okay. First of all, I'd like to thank Miso for the kind introduction, and also thanks Alice and Paul for organizing such a fantastic platform, so the world can hear the voice from the young researchers like us. So I'm so honored to present our recent work. The title, yes, as Miso mentioned, this is 2D materials for the sustainable world. Yeah, this is a pretty big title. Okay, so I cannot cover everything there. I just show in three aspects. So in which way that our 2D materials can contribute to the sustainable world that can make our world greener and greener. So that's three topics are electrocatalysis, the low power electronic devices, and some fancy things, the machine learning. This is my outlines. I will first of all give some brief introduction on the 2D materials, especially the 2D transition metal chalcogenides. And I think the main part of my talk will be the three examples, okay, how we can use 2D materials for sustainable world. They are self-gating in electrocatalysis, and the second one is ultra low power consuming devices. This is a negative capacitance-based field effect transistor. And the last one, we will use machine learning to guide us to grow some novel materials that will dramatically save the time and the money, yeah, and the cost. Okay, I believe most of you have very good background on the 2D materials. So simply put, 2D materials is the layer structures of the material, okay, and they always have most of them have the bulk counterparts. So the most famous 2D material is graphene, right? So graphene is the counterpart of the bulk material is graphite. So if we pick a the thin slice of the carbon layer from the graphite, we call this is graphene, single layer graphene. And actually, most of the 2D materials have the same nature. Yeah, they can be stacked. They are layer structures, although they have different phase, which I will mention later on. Okay, there are now so many materials on the, so many 2D materials, right? So many work on the 2D materials. So we ask ourselves, why this topic is so hot? Why we are working on it so much? So I conclude, summarize three reasons. The first of all, the numbers. I think the number of materials is critical for its applications, right? In terms of the 2D materials, we have a lot of candidates. So from the calculation, there are more than 1,000 of 2D materials. Here, just classified by the number of elements. I show some of them, such as for the single element, we have the star material graphene, a black phosphorus, and the boron-based, silicon-based, tin-based. And there's even more candidates in the binary compound, such as the nitride, sulfide, selenide, telluride, and oxide. So the one I will talk today actually is one of the subsets. They are transition metal dichotomize. We are usually short for TMDs. So they are consist of this sulfide, selenide, telluride, and there are more than 40 members of the candidate. They have a lot of fantastic properties like they're metallic, semiconducting, and insulating, and even superconducting, and as well as the 2D magnet from them. Okay, and apart from them, we have actually have other 2D materials with more elements like this ternary one, Bison, and also the alloys, as well as some more complicated structures. And actually, even now, every day, there's new 2D material has been discovered and been studied. So this is a really nice trend in these areas. So this is I mentioned the numbers is important. We have so many things to study. So which means we have a lot of applications that we can solve for. The second one is about the nature of the 2D materials. If you look at the paper, right, the paper has only two sides, back and bottom, the top and the bottom side. So the 2D materials is the same thing. There's no bulk property. So all the property from the 2D materials is from the surface. So the surface dominates the overall property of the material. And then the third one, the paper is flexible. So as to the 2D materials, which is also flexible, we can stack in the 2D materials one by one. But I would like to mention that we can make in the new material by stacking two different 2D materials. Okay, for example, we can transfer a material A to material B, and the resulting material is not A plus B. It's a totally different material due to the interlay interactions. So here I call this 1 plus 1. It's not 2, it's more than 2, it's different 2. So by doing so, we can design the material from the bottom. And this is also the dream. This is also the dream, I think, tens of years ago. Okay, within these materials, there's many applications. So in terms of the application development and also the industry prototype, I think this is our goal, the final goal. But currently, I think we are still in a preliminary state. Most of the material we need to figure out a nice way to make high quality in other areas samples. So okay, how many methods we can use to produce the 2D materials? Here I shows 4 typical ways. Okay, CVD method, chemical vapor deposition, chemical vapor transport, CVT, MOCVD, and the PLD. Okay, they can be used for the growth of different 2D materials. Here I just show example in our lab. So we modify the CVD method by drilling 2 holes on the micro oven. Then we insert the cold tube inside. So by turning on the micro oven, so we can realize a new version of CVD furnace, which can reach to a very high temperature, more than 2000 degrees. So by doing so, some 2D material with very high point can be realized. Okay, so this is how do we produce the materials. And our lab started working on this 2D material since 8 years ago. So we start from the sulfide, then we step into the selenide and the telluride. And then recently, we have realized the growth of a library of the TMD materials. And looking forward, there are 2 directions we're now going. The first of all, we want to propose some high throughput or or machine learning methodology that we can grow the materials more efficiently and with low cost. And secondly, we are targeting to the growth of the wafer size and the high quality 2D materials so that it can be really used in the practical applications. Yeah, and till now, our lab has grown more than 50 or 60 2D materials. So based on them, I think this is a valuable library for us. We have 3 directions. The first one, we are using the 2D materials to look at their conductor physical properties. And the second one, we are using 2D materials as a model system. We are looking at the electrochemical interface, and we're also trying, once we got some information from this, once we have a better understanding in terms of the electrochemistry mechanism, we want to use them to optimize the design of the new kind of catalyst. And yeah, in terms of the applications, we mainly focus on the electronic and optoelectronic applications. Such as the low power consuming devices, the broad infrared detectors, and so on and so forth. And today, yeah, as I mentioned, I will give it to 3 topics, right? One is this electrochemical interface, and then the second one will be the low power consuming devices, as well as the AI-based material design. Okay, so these are the first topic. This is how do we produce the 2D materials? Okay, this is just a brief discussion on that. So before let's say that 5 years ago, it's still very challenging to make 2D materials, the 2D transition metal dichotomized. I think the reason is some of the precursors here, the metal precursors, they have pretty high melting point. But however, the counterpart, the 2D layer, has a much low melting point. I'll give you an example: the hafnium oxide, right? If we want to produce hafnium sulfide, hafnium telluride, so this layer structure, the melting point is around 700 or 800 degrees. However, the precursor, the hafnium oxide, has a much higher temperature, melting temperature, which I think above 1,500 degrees. So this is main challenging. And when we look at the growing procedures, we realize there are two key parameters that dominate the growth. So the first is the nucleation density, and the second is the reaction rate. So how can we control it? So one of my students now, here's my postdoc, Jia Dong, he proposed that we can add salt into the precursor. So molten salt has been usually used in ceramic industry, right, to lower down the melting point of the precursor so that we can get nice ceramic, shining ceramic at a low growing temperature. So we borrow this idea for the growth of the 2D TMDs. And surprisingly, we can grow almost the whole family of this transition metal dichotomized. As you can see here, we show there are more than 30 different candidates of TMD, from moly, tungsten to iron. And most of them that are quite thin, are more than half, we can grow them into monolayers. And then we look at the structure of this material. It turns out for the monolayer TMDs, they're primarily 4 phase: 1H phase, 1T phase, 1T prime, and 1T double prime, depends on the position of the ions. And not only for this binary 2D materials, we apply this method and successfully grow some alloys, which including the ternary alloy, the quaternary alloy, as well as the heterostructures, so which shows this method is quite universal. It can produce almost unlimited candidates of the 2D TMDs. I take one of the alloy as examples here. So this is an alloy with 5 different elements. And if you look at the scale bar, these are pretty small areas. It's less than 10 by 10 nanometers. So it's incredible to put 5 different elements in these small areas homogeneously, okay? So there's no phase separation here. Okay, and what's the role of the salt? And we found that salts may react with the precursor, such as the oxide precursor, and they will lead to an intermediate product. And this intermediate product is highly activity, has very high activity, and so some of the 2D TMDs will grow pretty fast, and in which result a lot areas of material as large as 1 millimeter size. Okay, so this is story about the growth part. Now let's step into the first topic. So how do we use the 2D materials as a model system to elaborate the mechanism of electrocatalysis for semiconductors? We know that the electrocatalysis has been an old subject, right, for more than 100 years. And even now in our daily life, we are using it, even we're not aware of it, right? So they are producing different fields for us, such as hydrogen, and they've been used to produce electricity. However, the most important part of the electrocatalysis is the catalyst, right? And now most of the catalyst is the noble metal. Okay, I'll give you an example. In order to generate hydrogen, we have to use the platinum, okay, PT. But you know, PT is very expensive. So people they propose, can we use alternative materials such as semiconductors that have a much lower price? So there's tons of work that work on these areas. But here comes a question. So the electric conductivity of semiconductor is actually pretty low. Yeah, if you look at this IV curve, that's a gating biased current of semiconductor, where we will realize if there's no back gate, semiconductor actually is an insulator. If it's an insulator, how come the charge can transport from the electrolyte to the electrode and to external source? So it's very challenging to happen. And this question has been proposed actually 40 years ago by Alan Franklin. He mentioned that semiconductors they are not ideal catalysis because they are low conductivity. However, if you look at the publications, so there's so many work on the top of 5 journals, and they using the nano materials, the nano semiconductor materials to produce to use them as a catalyst and realize really high performance. So what's the reason? How come there's a contradiction? In order to address this, so we design a new platform. We call this this is a in situ platform based on the micro electrochemical platform, which enables us to collect the electric signal and also electrochemical signal at the same time with a pretty high resolution. So the resolution is 3 times order higher than the commercial equipment. Let's take a look at the real device. So this is our device. If we zoom in here, okay, we have a job here. So this job is electrolyte, and then we have the reference electrolyte, the counter electrolyte, and let's even zoom in here. Okay, here we go. This is a window, right? Within the window, these purple areas, they are the catalyst. They are the active material which get involved in the reactions. And outside of the window, they are all protected by PMMA or other materials, so that we can make sure the interaction can only happen in such small areas. So this is ideal platform for us to look at the mechanism for electrocatalysis. Okay, what are the results? Okay, what is the structures? If you look at the interface, okay, during the reaction, we have different ions that will accumulate at the interface, either positive ions and negative ions. And here, this area is semiconductor, right? So this structure can be simplified as a triangular quantum well, triangular potential quantum well. So by resolving this equation, we will have such a solution. If you look at the solution, it's quite surprising. Yeah, there's only one parameter, the thickness. Look, H here, the D, the thickness, right? It only depends on the thickness of the semiconductor. While others, like mass, like Q, pi, they're constant. If we substitute the values to the equation, we will realize, yeah, this thickness, okay, is only about 10 to 30 nanometers thick, only up to only about 30 nanometers thick. If above 30 nanometers thick, the state, there's almost state in here. So which means we call it surface conductance. To demonstrate, so we have done a lot of experiments. We fabricate tens of the device with different thickness of the semiconductor. And we put them together. It turns out at the surface, we have the highest current density. While if we go into the surface, like 15 nanometers, so the current will reduce by, or reduce to 1/10 of maximum one. And at 25 to 30 nanometers, we get almost no current there. So which means the current, okay, during the electrocatalysis reaction only pass through along the surface of the semiconductor. It won't go through the bulk of the material. Okay, so based on this idea, we propose a new concept. So we know that in the nanomaterial research, people always say, okay, because our material is nanomaterial, we have very high surface areas, so the performance is good. Performance of this, performance of that. Here, we would like to add one more term. And not only for the surface, it's also because of the surface conductance. So let's give examples, right? For the bulk material during the reaction, only the surface will get involved into the reaction. However, if we break into the small pieces, the nanomaterials, so we will have a few orders number of the nanomaterials, and each flake will carry almost the same amount of current. So the total current will be dramatically higher than the bulk one. And we believe this is the reason why the nanomaterial-based semiconductor has such a good performance comparing with the bulk one, in addition to the high specific areas. And actually, high specific areas is the reason for the high surface conductance. Okay, so let's move forward to the second topic. The topic about how we use the 2D materials to build the low power consuming electronic devices. We know that the semiconductor market is pretty huge now and it's growing every day. We are surrounded by it. I believe many of you cannot live without it, without the cell phone, without computer. Okay, if you look at these semiconductor electronic devices, the core part or the key part is what? Is transistor. So this is a simplified transistor. And what is the power of the transistor? If we would like to operate it, yeah, the power is proportional to the square of the working voltage. Here we call VDD. So VDD, yeah, let's look at this figure, scaling challenging. You realize since 30 years ago until now, we are pushing the VDD from a few volts to 0.7 volts. And unfortunately, we cannot put even smaller. This is because this number is determined by the nature of silicon. So we cannot cross a bar. We cannot cross the physics law. So 0.6 is the minimum, is the limit of the VDD. So it's a very challenging now. We cannot break the wall here. So, however, now we propose some new architecture that may realize even lower VDD. One of them, we call this is the 2D negative capacitance field effect transistor. So 2D NCFET. So this architecture, we need two kind of material, the 2D semiconductor and also the 2D ferroelectrics. So by combining them, we can realize a pretty small steep slope and also very low voltage, which can be down to 0.2 volt, even lower. So if we substitute this value, 0.2 to the equation, so we can simply get a conclusion that if we can use the 2D CVT to make a circuit, we can save more than 90% of the energy. Okay, so in terms of the materials, now we have a lot of the 2D candidates here, and also we have a few good 2D ferroelectrics, such as the CIPS. I think mobility will be very important parameters to build a transistor, right? And until now, from the calculation, we know some of the 2D semiconductor, they have good mobility, such as the tungsten sulfide, the moly sulfide. And the good thing is they are also very stable. And yeah, we measure some of the typical 2D semiconductors, such as the N-type moly sulfide, P-type tungsten diselenide, and this is business oxygen selenide. They all have nice mobility that is almost comparable with silicon. And apart from them, we even have even more candidates now we are looking at for the 2D semiconductors. And some of them have very high mobility, like the tellurine. I think the community is also looking at these materials, and also the black phosphorus, although it's not that stable. So the next step, okay, let's make a device. So here we fabricate a simple device by building this. We're using two transistors to build it, and it turns out we can realize a very low subthreshold, very steep subthreshold, which is below 60 millivolt per dec. So this is already below the theoretic values of silicon. And we can even push the working voltage, which we can push it down to 0.1 volts. It's still workable here. And I think the next way is to make the wafer side of the 2D semiconductors and realize the small scale, middle scale circuit for the future applications. And in terms of the semiconductors, okay, there's one more thing. It's also very popular now, flexible electronics. Here I share a video with you that there's a tree, and surprisingly, all the leaves are made of the flexible screen. So that's the power of the technology. And I do believe you are using the flexible electronics right now, right? Such as the iWatch and the different band, right, with you. And there are great application, promising applications for the flexible electronics. But again, the problem is, I believe you have the experience, right, with Russian for the chargers. So most of the flexible electronics, they cannot stand by for a long time because of very small batteries. So I think this is, again, we go to the original problems because of the power efficiency of the silicon-based device, because all our electronic devices, including the flexible one, they are made of the silicon-based CMOS. Okay, so here, as I mentioned, right, 2D material is naturally flexible. So how come we use 2D materials to make the flexible electronics? So it's quite a natural thing. So we fabricate a demo here, and it turns out it works very good. We can achieve the very steep subthreshold, which is below 60 millivolt per dec, and we can also bend it with a quite small bending radius that is less than 4 millimeters. Okay, and perhaps we can look at this question or this semiconductor-based question from a different angle, the history angle. We know that 30 years ago, like 1985, there are only 10 materials, a dozen materials being used to make the circuit, to make the transistor. And now, imagine how many of them. So we're now using almost 30 different elements in the periodic table. Okay, so if we would like to push the limit of the transistor, of the semiconducting architecture, I believe we need more elements to get to play in this playground. And here, the TMD will be a very strong competitor here. And if you look at the architecture, so we will realize that at the very beginning, we are using the planar FET, and next, it evolved into the FinFET. Look, this is the semiconductor. It's look at the fin structure. And the next step, maybe a few years later, we have found the structure in our CPU. This is a gate all around. And if we look at the trend, what will be the next? So the ultimate or the final version definitely will be the nanosheet based. And the 2D materials is the thinnest nanosheet. So 2D materials will be, I believe, in a few years, in a key player in the 2D semiconductor. Okay, so let's watch a video. This is from Samsung, which shows how the FET revolution. This is not the advancement, just to share some information with you. Yeah, we start from the planar FET. And the short chain effect to make limited the performance of the circuit. And then we step into the FinFET, which we use more surface areas there. And the gating effect, the gating is more efficient. And the next, we expose more areas. So we get gate all around. So after gate all around technology, so the 2D materials, they will be here. This is the MBC FET. And now if we reduce the structures of the thickness of this MB, where it is, yeah, the thickness of this MBC, finally there will be the 2D form. Okay, so I think the last topic I'd like to share with you is about how we use the machine learning to help us grow the novel materials. Here I call it smart analysis and smart growth. If you look at the history of material production, material design, there are 4 phases. Many years ago, thousand years ago, we are just using the raw materials, using our hand. We can craft some materials, some tools, but still very rough. And 100 years ago, now we have very nice technology that we can refine the materials. We can engineer the material to some extent. And these years, in the past 10 years, we have advanced technology and a very cutting-edge equipment that we can fabricate the material in nanoscale. And what will be the next? So I believe in the future, driven by the machine learning or the AI technology, the material development will step into a new era. Okay, so how machine learning can help us to produce the new materials? If you look at the material informatics, okay, so this is a very classic 4-step. First of all, we predict the property of the materials from some database, and then we optimize the parameters. And then next, we try to grow the material. This is trying and errors. And then finally, we use the material in the real device. And yeah, you may realize step 3 is the most time-consuming and the most energy-consuming part. So can we use machine learning for this part? If you look at the growth of material here, in organic material, we know that we have used different precursors. We have different here, the growing parameters, there's a macroscopic parameters. Some of them is very challenging to control for the advanced materials. However, if we input or input these parameters to some models, if the model can tell us the optimized or the best parameters, so we should be able to save a lot of time, right, for the test and trial, for the trial, for test and trials. Okay, so what we do here, we propose here this model. We call this a progressive adaptive model. So within this model, we can start training the model at the very beginning. The start of the experiment, we feed in the parameters. Even if it fails, it's also valuable. And then by repeating this, we can reach to optimize green parameters I'll give you an example, okay. If without this model, we probably need 100 of trials. However, with this model, we can save 50% or even more time to find the best parameters for the material growth. And the second trait is the smart analysis, right? Because some of the analysis of material, they are also time consuming, such as the FM. You have experience, right? You take a long time, hours to get a nice FM image. And also the TM image, it's not an easy job. However, if we use the machine learning method, for example, use machine learning to tell us the defect concentration of the material, it will be very helpful. And this step within the help of machine learning can be reduced to a very short time, even down to a few seconds. We can realize that we can finish this. Yeah. So by employing this progressive adaptive models to different dimension systems, such as the 2D, 1D, and the zero-dimension system, we believe this model is capable of doing great job in terms of saving the time for looking at the new material, find the good parameters. Okay, I think this is my last slide. Apart from the soft part, I just mentioned the software, right? How do we use machine learning to drive the growth of material? We are trying the hardware way that we are using the 2D materials to design hardware structures to realize this neural network functionalities. Okay, so if you're keen, if you can go take a look at this paper, which we collaborating with our colleague, Nuripan. Okay, I think that's pretty much my talk. Here, I would like to thank all my group members. So they're so smart. They're also very hardworking. So that they can make things happen. So so that we have a really nice potential applications of the 2D materials. And I also would like to thank the financial support from the government and also my university, NTU. Okay, I think that's pretty much my talk. Thank you very much. I'm looking for your questions.
Well, thank you very much for your, it was such a really informative talk, and I love your passionate voice especially. And thank you. I learned a lot.
Thank you.
So this is the question from the audience. The first one is, it is amazing for your evidence of surface conduction. From your plot, we can see that it becomes huge under 10 nanometers. Is it shown on other materials or just certain materials?
Yeah, this is a very good questions. First of all, this is a general effect. This is a general phenomenon. It's not only for our material, molybdenum sulfide, TMD. We show that it applies to all the semiconductors, and even not for the 2D material. It's also for the bulk material. So this is what we call surface conductance. As long as there is electrocatalytic reaction happens, okay, as long as the materials will show a good performance, so the surface conduction will be there. It will be there. And nearly to the surface, we have a higher high currents, and deep into the bulk, the current will dramatically exponentially decrease. So that's what I said, that that current will only within 30 or 20 nanometers, because if we go deeper, more than 30 nanometers, there's no current, and the most of the current will be carried out at the most top surface, the superficial areas, the top 5 nanometers.
Okay, good. So we'll go to the next question. Is it on? Not yet. So I can read it from, oh, okay, here. Professor Liu, fantastic talk. Our group follows your work for a few years. Congratulations. As you said, for silicon material itself, it's hard to push down the power consumption. 2D materials are good candidates. How about your opinion on mass production of 2D materials?
Okay, this is also a very good question, and it's also a question I always ask myself for a few years. So I think the main challenging for the community is still on the large scale growth of the 2D materials. Okay, so there's so many 2D materials by far. Only a few of them, such as graphene, now we can realize wafer size growth or tens of inches growth, right? But however, for other materials, including the TMDs, we can only grow it like tens of microns. Some only a few, like molten sulfide, there's a work report they can get wafer size, right? Yeah, so the growth is still a big challenging. I think the main problem is we are still not exactly understand the growing mechanism for most of the 2D materials. Look, graphene is only one material, one element is carbon. So even though the community spent, I think more than 10 years to figure out what happened. And if we take a look at the other material, binary 2D materials, it's very complicated. And if you look at the CVD method, we have the precursor and then we substrate a different place. So that is why it's so challenging. But however, we see some promising ways that we can grow wafer size or massive production 2D materials, like CVD method. So this is very promising for the wafer size growth. And I like to add one more point, as size is one point. The other point is quality. Yeah, we have to make sure not only the size is the scalable size, we have to make sure the quality is good enough. Here, I mean quality, I'm talking about the defect concentration. Yes, we have to make sure the defect concentration can reach to the electric rate so that we can integrate the 2D materials into the electronics. So yeah, if we can satisfy these 2 points, I believe that the 2D materials will really play the role in the semiconductor industry.
Yeah, I look forward to the next 10 years for the mass production of 2D materials, especially from your lab. So the third question, dear Professor Liu, in the AI model, how many parameters you considered?
Okay, how many parameters you consider? Currently we consider for the material, for the work I shown, right? We consider around 10 parameters. Yeah, this is not a full, this is not a complete set of the parameters. We know that. So if we count all the possible parameters, I believe there are even more than 100 parameters for the growing of new materials. So I think our next step in our future plan, we would like to build a general model that will consider all the possible parameters for material growth, so that that model can be generalized to not only to the 2D system, but to the all other inorganic systems.
Okay, so it's time to deliver this certificate. Big congratulations again on being selected as the ACS Nano Rising Star. I'm sure you really deserve it. and we are so proud of you. And in the online that they did, the file of certificate will be delivered by email in a few days from Alice, I'm sure. And thank you
Thank
so
you,
much.
Michelle. Thank you, Michelle. I'm so excited about this. Actually, we have published more than 20 papers on SS Nano.
Oh, okay. Okay, we are back.
Thank you, Michelle.
And we're looking forward to more.
Yeah, of course. We will continue contributing on it.
Well, welcome to the panel. You haven't met Professor Shelley Claridge yet, but she'll be giving the third talk today, and we're looking forward to that. I'll give her a formal introduction before that talk begins. And one of the things that our audience, which is now already over 300,000 people live, sure wanted to know was how each of you put your career trajectory together during your training. So we have many students and postdocs who are online, and maybe let's start with Professor Zheng. When you planned out your PhD and your postdoc and the research topics, what were you thinking about where you'd like to go ultimately, and maybe share what you learned along the way there?
I think you're.
I think you're muted, perhaps. Yeah.
Yeah, I can on it, but I'm not sure I have got the question. So the question is about my personal experience for studying, or when I have some new student. So I'm not sure.
Oh, we were asking about you personally. When you chose your PhD, your group for your PhD and for your postdoc, how you did that, and how did that map into your the career that you've made so successful when you joined Tsinghua?
I see. Thank you for the explanation. Actually, at that time, I do not think much. It's not well planned. My PhD is finished at it's almost it's 13 years ago. I got my PhD at 2007. So I entered Peking University. It's Beijing University at 2002. At that time, actually, I have very limited lab experience. I just know that Professor Zheng Liu is my tutor for my PhD. It's very famous, and it works on nanomaterials. At that time, nano is a very, very fancy and new word. So I joined his lab with very limited knowledge about nano. But since that time, I learned a lot of nanochemistry and carbon nanotubes. So when I got my PhD at 2007, I think I love carbon nanomaterials very, very much. This is the materials I most love. So I continued my postdoc at a lab in United States, which is also focused on carbon nanotubes. But the format of the carbon nanotubes are changed from the individual carbon nanotube from my PhD study to carbon nanotube fibers. And during my postdoc life, I'm more independent because my tutor gave me big room of freedom, so I can decide the direction and the details of my research. At that time, I read a paper on stretchable conductor. It's more than 10 years ago. So I think, oh, flexible electronics is very fancy, and I would like to try using nanocarbon materials for flexible materials. So after I published the paper SS Nano 2009, I using that carbon nanotube materials produced in the SS Nano paper, I designed another materials as a stretchable conductor. It's published at Advanced Materials at 2010. So this is the start of my research on flexible electronics. So after I back to China, I'm looking for positions, and occasionally I know that there's a position in Tsinghua University. So I joined Tsinghua, and I still love carbon materials and flexible electronics. So I keep working on it. So about 5 years ago, I know more about silk materials. So I tried to combine nanocarbons and silk to use them combination to design composite for wearable materials. So this is my experience. I'm not sure if it's helpful, but it's really it's the fact. Thank you.
Sounds very curiosity driven. So let's go next to Professor Claridge, who picked up many different fields along the way in her training, and tell us something about how you mapped from where you went in biochemistry and math and other areas into what you do now that we're about to hear.
Yeah. All right. Can you guys hear me?
Yes.
Yeah.
Okay, perfect. Yeah, so as Paul was saying, my undergraduate degrees were actually in math and biochemistry. And when I graduated, I sort of wanted to do something different. And so I actually went into software engineering. And at that point, I had never programmed, but the industry was young enough that they would take people who had limited or no programming experience if you knew how to do math, which meant to them that you knew how to think. So I worked in software for 6 years, and then I decided that I wanted to do something that I found really fundamentally exciting. So I talked to several professors, and the chemist had the best answer about what they found exciting in their field at that point. So I went to graduate school at Berkeley and found myself in a research project that dealt with building structures at very small scales, combining biology, which spoke to my biochemistry background, and inorganic nanostructures, which were new to me, but were of potential use in electronics, which sort of spoke to my software engineering background. And I think from there on, a lot of my career trajectory has been built on frustration. So by the end of my graduate work, we'd been designing these DNA scaffolds for inorganic nanocrystals. And sometimes you'd put them in the TEM, and this beautiful scaffold that you designed to put the nanocrystals here and here and here and here, the nanocrystals are all kind of clumped together over here. So you can tell something is going wrong, but something is going wrong in the part of the structure that you can't see. So I decided that scanning tunneling microscopy would be one of the few ways of getting structural detail from organic matter, near the atomic limit. And I was a postdoctoral researcher with Paul, designing new scanning tunneling microscopy instrumentation to do microwave frequency bias modulation to probe local polarizability, which is a way you can get chemical contrast. When I started my independent career at Purdue, we had planned to take that project sort of in a new direction and to try to tackle more complex biological structures. But there was an early experiment that we did in my lab that was meant to be a control experiment. Basically, we made this surface chemistry that had some hydrophilic and some hydrophobic sections that were meant to trap molecules that would reside across a cell membrane in a certain orientation. And that experiment was really hard. It was really frustrating. So we got interested in why it was frustrating. It turned out the reason it was frustrating was because water was binding to the surface and it was making it very difficult to do STM imaging. And so at that point, we sort of had two choices. We could figure out how to dig in and use STM to understand biological structure in that way, But we ended up going in a completely different direction that has allowed us to deal with scaling issues, like do surface patterning up to very large scales, which is something I'll talk about today. It's allowed us to deal with many different kinds of surface chemistry. And so it's addressed another form of frustration that I had as a postdoc, which was that there's so much detail in a scanning tunneling microscopy image, but getting outside that level of detail, scaling up is very hard, because the STM works at very small scales, but it's hard to make that imaging modality work at larger scales. So I think, every time I get frustrated by a problem, that's when I know we're going to get something really new to work.
That's very encouraging. And Professor Liu, maybe you can tell us about how your trajectory took you to where you are.
I think my career path is quite smooth. I was working as a postdoc, as a student in NCNSD, this academic science. And at that time, I was working on the carbon nanotubes, like Professor Zhang did. But I did not that good job. I was growing the carbon nanotube arrays. I spent 2 years, and still I cannot get the single wall carbon nanotubes. So that's really a frustration. And and my last year of my PhD, that time the graphene appeared okay. And the graphene is also a new type of carbon materials. So I tried to grow graphene and do something about graphene. So I think this is overall my work on my PhD. Nothing really important to say, but at least I'm touching something that cutting edge, the frontier of the research community. And by the last year, I have a very good opportunity. That time, Professor Zheng, he visited us, and we talked a bit. And then I got an offer, postdoc offer from him. So after a half year, I went to Rice University, so working as a postdoc in Professor Zheng and Professor Zheng Liu's group. So I also say that I'm working for both groups, one salary, just for joke. But the good thing is, I can bridge the things from the two groups. I can learn a lot of things. So I got a fantastic postdoc training. So I know what is material, how to characterize material, and I know how to fabricate device, working in the clean room day and night. So I think this is a pretty important, critical state for me, so that I can step into the faculty career smoothly.
Mm-hmm. I think all three of our speakers made clear how much thinking along the way is, and also that paths are not direct. Mm-hmm. So look for those blocks that turn out often to be opportunities later.
Yeah.
Yeah, I can summarize. One is curiosity driven, and one is frustration driven, and one is opportunity driven, I guess.
Sometimes all combined in one. Yeah. We've said this a number of times at the talks that you get to see everybody's successes when they give a lecture, but part of what we like to do in the panels is talk about what real life is, right? Often those successes are a small fraction of the time, and there's a lot of frustration along the way, but you don't get to see that usually in people's papers and people's presentations. So perhaps let's continue a little further along those lines, and we'll start with Professor Clarence this time. What do you wish you knew in your training based on what you know now?
That's a really interesting question. Because actually the work that my group does now almost exclusively uses techniques that were never part of my training. So I think, probably out of my training, the most important thing has just been the sense that I can learn new things. And so I think if anybody is looking for an overarching principle for what you should be learning is how to learn, and how to learn when there's nobody there to teach you that thing. Because when I came into my lab here, we built up a scanning tunneling microscope, and then almost immediately we transitioned to using AFM imaging predominantly for characterization, and then to SEM, and now to fluorescence, which I'll be talking about today. And now we're starting to grow cells. And so, some of those things you can do through collaborators, but some of those things I think are actually much easier to integrate into your workflow and to use in new ways if your group understands how to use them. So I think, every year we're fundamentally changing the things that we focus on. And that's something that I love, but it means a lot of relearning at every step. So I think that's part of preparation that sometimes is not as clear when you start graduate school, because it seems like you're going to learn this set of knowledge and you're going to be really good at this thing. But the thing that you need to be good at next year may be something very different.
And Professor Liu, let's go to you next.
Yeah, I think I encourage my students and postdocs to learn as much as possible. Okay, don't focus on your own areas. That's really narrow. The more you know, you touched, okay, the better opportunity you will find to collaborate with others, and or come across some new ideas. And yeah, I think this one thing. The second one, I think all the training behind all the training, I think the logic or rational thinking is the most important. So how can we arrive in a conclusion from the experimental phenomenon? And if we see something, how can we demonstrate? So using in which way we can demonstrate, and as well as how to write a paper. So what is the structure of the paper? This is actually all about logic, right? And how to reply to comments, right? So I think this is the most important thing I told my students. So logic, radical thinking.
Very good. And Professor Zheng.
Yes, I agree with Professor Liu, actually. I think during my training, I think if I have more training on the independent thinking, it will be better. And also how to, besides my own research, I should pay more attention on the researchers of the people around me. So learn how to collaborate and how to contribute to others' work. So now in my group, I always encourage my students to come up with independent ideas, especially for the student after 2 or 3 years work in the lab. So most of them, I only give them a bigger direction, and they will think more and find opportunities based on their own experiment and own observation. Till now, I think this works better than I just give them a simple project.
Very good. Yeah, we we also encourage our group members to spread very broadly into other topics and take advantage of. We're all at universities that have very great breadth, and under normal circumstances, there are talks all over in many different fields. But I think one of the opportunities for people during this special time are talks like what we're hearing today. One can go to a conference, number one, without paying registration, and learn about a field. And there are opportunities all over the world every day. And so by looking outside your field at your interests, I found that's been one of the best guides for where we've taken our group and where our students and postdocs have ultimately found what they're interested in. I think students and postdocs ought to know that you're not restricted to what you did in your training. You've heard how there's an arc, in the trajectory of what you do in science, and you can change. One of the wonderful things about academics, if that's your goal, is you can change fields very dramatically. What we do now and what Professor Claridge did with us is absolutely nothing like what I did as a graduate student. Is even in a different phase of matter. And we heard a beautiful lecture from Professor Kim in our first round of ACS Nano lectures about how one moves from one area into another, and is driven by that I think curiosity.